Okay, so it's recording. I think it's good to go. Yeah, if you guys noticed, this week's notes are really fancy. So shout out to my friend Meeps. She actually did the drawings for everything. So hopefully this brings some good vibes and whatever we're going through right now. I don't know, when I saw like the bees and the flowers and everything, I thought like, hey, I kind of miss that, you know? So at least we get to see them virtually. Hope you guys liked it. Okay, all right. Today we are going to talk about alpha carbon, right? Will you putting that? Yes. Oh yeah, one more thing. Okay, so for 234 quizzes, if you get the email from your TAs, right, you can just take a picture of your cell phone if you don't have a printer. And if you have a tablet, by all means, go ahead and use that. But if you don't, you can just write the answers on a piece of paper, snap a picture, send it back to your TA. Okay, that's also fine. All right, so let me see. All right, who here has issues with alpha carbon? Because the last two lectures were pretty abrupt, right? Especially for Dr. Molina's class. You guys only went through like 3/4 of it. And then for Dr. Driver, I don't know if he experienced technical difficulties as well. So I felt like it was really disruptive. I'm really hoping that today we won't have that much of an issue. We'll just have a proper review, okay? And hopefully today will also help you to fill in the gaps for whatever you don't know. And for those who have yet to learn all these stuff, right? We'll finish them off on Tuesday's lecture. Okay, so let's just go back to basics, right? What this chapter is about, and you need to be able to identify what they are, okay? It's all about alpha carbon, so it pertains to the carbon that's adjacent to the carbonyl, right? I've already marked them out for you here, okay? And do take note that you need to sometimes identify what the beta carbon is, because if you have a double bond, right? If you have an olefin going down this way, right? You can have a 1,4 addition, right? Alpha beta unsaturated. So this is where you need to identify where the beta position is. Okay. So what's the key point? Carbons next, it's just one line, okay? Carbons next to carbonyls are reactive, okay? They are reactive, and what you want to always look out for is your enolates. As an intermediate. If you don't have an enolate in your mechanism, you're probably doing it wrong. You are going to hear me saying your enolate flex a lot this chapter, because this entire chapter, you're just going to see lots of this here. You're going to have to flex them out. I'm going to keep nagging at you so that you remember what your mechanisms require, okay? All right, let's move on to enols versus enolates, right? So in Orgo 1, last semester, you learned that this was an enol, right? And what does it do? Is it stable? What was that thing that I said before you can even blink, something happens? Yeah, exactly. It will tautomerize into the keto form, right? So this is something that we have for enols. Now, for enolates, though, okay, enolates, on the other hand, are reactive, right? They are hiding a nucleophile through here. Okay, this is what is going to be the reactive part of the molecule. So again, this doesn't really tautomerize per se because you need an enol for that, right? But if you have an electrophile, right, this collapses down to attack to form the electrophile here. Okay, so what do you think we are gonna do here? We are actually gonna elongate a carbon chain, right? So another way of elongating carbon chains. Okay, so we have learned alkynes on the very first day, and then Grignards, right? And then we did EAS, we did conjugated pi systems, and now this is just one more way for you to make a chain longer, and that's through alpha carbon chemistry. Okay, we are leveraging on the nucleophilic nature of the alkene to put on electrophiles, and that will be our long carbon chains. Okay, make sense so far? Please know the difference. Okay, so in this chapter, you're going to encounter 3 types of main bases. The first one being potassium hydride in 18-6, right? And this base here is going to be thermodynamic. So it attacks the more or less substituted site. Good. Right? It attacks the more substituted site, and this is an irreversible base. So what does this mean? If I had my error pushing mechanism, all right, my hydride is going to attack the more substituted site because this is a thermodynamic base, and it's going to form my enolate. Okay, and this here is a single arrow, right? Because this is irreversible. Now, what about Naomi and her homies or the other derivatives of it? Sodium methoxide with ethanol. This is also thermodynamic. Okay, but this base is reversible, which means when you draw an error pushing mechanism, okay, it's gonna also attack the more substituted site. Right here. So Omine is gonna come in, right, to give me my enolate here. But don't forget, this is a reversible reaction, so you have to put 2 arrows. Okay. Do you remember when I talked about Naomi and her homie being basic, right? That was back in Argo 1, and she's a big SOB this semester. Why? Because she can't make up her mind, right? It's going back and forth. So this is how you remember her behavior in this chapter. Okay, it's really important because if you don't put the double arrows, you are going to get points taken off. It's a really, really crucial thing that they emphasize on for some reason, reversibility. So please take note of the 2 arrows, okay? All right, and then the next one we're gonna do is something I actually suddenly introduced to you back in Argo 1, around the same time too, when we're doing alkynes. What is this here? This is a base, right? Remember we were dealing with sodium amide back in Argo 1 to deprotonate, and I'm like, oh, guys, stop being boring. I have no more sodium amide in my lab. What other bases might you encounter, right? And do you remember me saying lithium diisopropyl amide? This is exactly why I did that, because at some point in Argo 2, you are gonna have to encounter it. So I decided I'm just gonna go ahead and show it to you first. I don't know if any of you guys remember that, but in this chapter, you are gonna have a subtopic entirely based on this base alone. Okay, so it depends. By default though, right? Lithium diisopropyl amide is what? Kinetic or thermodynamic? Yeah, exactly. It's kinetic. So if you don't see equivalence specified, right? Or if you see 1.05 equiv or unspecified, it's going to be a kinetic base. But at 0.95 equivalence, right, this base now becomes thermodynamic. Okay, and this is how you have to specify in your reagents if you were asked to predict them. Okay? You are able to use all these three bases if you need to have a thermodynamic addition, right? But make sure if you choose to use the LDA route, oh, by the way, this is called LDA for sure. If you choose the LDA route, you have to specify your equivalence. So is there a way to identify if a base is reversible or irreversible? It's only Naomi, basically. Everything else is irreversible. Okay. And this base by default is also irreversible. Okay. So just take note of the behavior of each of these bases, right? If you choose, for example, I don't know. Okay, let's try this here. If I say, right, 1.05 equivalent, so we know it's going to be kinetic, so it attacks the less substituted site, right? It's going to form my enolate right here. And because this is an irreversible reaction, I only show one arrow. Okay, yeah, I'll talk about when to use an irreversible base and reversible base later on as we go. All right, every semester, I see students doing something like this. This is iffy. I wouldn't touch this. And definitely, I would never do this. This is wrong. Please don't do this, okay? Don't ever put LDA with a negative charge because we don't know. Nothing in LD or A is basic in nature, right? But what makes LDA basic is the fact that the nitrogen has a lone pair. So you have to show the full structure. Put an N, parentheses, IPR2. Okay, don't put R, and most definitely don't put LDA. All right, so why do you make that? Oh, because remember, when you have an excess of LDA, it becomes kinetic. And by default, LDA is a kinetic base. Okay, but we can force it to become a thermodynamic base with just 0.95 equivalents of it. Make sense? And I'm not going to go through the whole mechanism on why that happens. It's already covered in your notes. And honestly, like, you're not going to see that in your exam. So I'm not going to worry too much about it. But just remember, a lesser equivalent of LDA makes it thermodynamic. No matter how many equivalents you specify, though, this base is going to remain irreversible for sure. Okay, the only reversible base that you see is Naomi and her homies. Okay, so let's talk about the basic rundown. So remember, we are using enolate chemistry to form carbon-carbon bonds, right? It's also another way to form rings. So if you see rings in your product and you're asked to predict the reagents, high chances are you're going to have to use something that's enolate chemistry based. Okay, so let's start with the first one, right? Remember, always first things first, always identify where your alpha carbon is, right? Or your alpha hydrogens are. It's going to be right in between these two R groups they are both equivalent, so it doesn't matter which way your enolate goes, right? Always show this first step though. Okay, and this is where you have your enolate formation. 5, 4, 3, 2, 1. Last chance. You guys owe me chocolate when I'm back. Okay, remember, it's a reversible reaction, so please put 2 arrows there. Okay, so because now you have an enolate, right? We have seen where the nucleophile is. The nucleophile is going to find the electrophile, right? So how does that happen? Remember, resonance always proceeds faster than the nucleophilic attack. My double bond is going to collapse down. My lone pair is going to collapse, right? And it's going to find my electrophile and kick off my leaving group to give me this product here. Okay, and because, remember, if you see a leaving group on both ends, always assume that Naomi is in excess. Okay, leaving groups in both ends, so Naomi is in excess. Another molecule of Naomi is going to come and deprotonate the other hydrogen there. Okay, so like this here, right? So then the cycle repeats itself. It collapses back down into a carbonyl. Then your alkene becomes a good nucleophile, right? So it's going to attack the electrophile, kick off the leaving group, and do you see we're forming a ring? For those of you who were with me over spring break for the reviews, I actually snuck in this example, right? I don't know if you remember. But how many membered rings are we forming? See here, 1, 2, 3. So we have a 4-member ring in that sense, right? Okay, so this is what we have here. Okay, now the next one. What kind of base do we have? Always, oh, this is also the next question you have to ask yourself. What kind of base am I dealing with, right? Because it tells me what I need to deprotonate. Very good. So only the last step, that's irreversible. Everything else in between is going to be reversible. Okay, so we have potassium hydride in 18 crown 6. So it's going to be irreversible thermodynamic. Okay, thermodynamic tells me that my hydrogen is hiding in here, and my base is going to be in the form of hydride, right? So I'm going to do it this way. I'm going to attack here, form my enolate. Okay, and again, I find my nucleophile in there, right? And I have an electrophile in the form of benzobromide. So what I have here, okay, and then if I were to treat this same step again, do you notice that even though it's thermodynamic, it's no longer, there are no longer any other alpha hydrogens available on the right? So what do you think the base would be forced to do? It will be forced to take away the one on the left, right? So this is where order is going to matter a lot, right? If you would swap the If you were to swap the functional groups, you're going to have them adding in the wrong place. And butyl 5,6 is a hexane that we're adding. And what we have here, hexane, isopropyl, phenyl. Okay. Okay, I'm gonna do a little bit of a weird thing where I'm gonna talk about malonic ester synthesis first, just because this is one other way that you can like explicitly see a chain getting longer, right? I know usually professors leave this to the last, but I'm gonna try to do it in the first because I have more important stuff to talk about later on, okay? So the hexane comes from here because this is N-butyl, right? Oops. This here. And butyl is 4, 5, 6, right? So it's a 6-member chain. So I'm just going to call it hexane. Does that make sense? Step 3E2. Okay, so yes, this is one more thing that I was not able to check before the review, I'm sorry. But for the most part, you will encounter this in your problem sets as well. I have no idea when does it favor an E2 and when would it be an addition, okay? Sometimes you might see this question on your problem set, right? Yes, technically you're gonna get an E2 reaction, but I just want to show you this because on your problem sets, there are questions that are like that too, right? And in this case, and when I checked the answer, it was actually an addition of a chain. So just take note that you could have either or. When I asked Dr. I think there was a student that asked Dr. Molina about it on Thursday too, and she even couldn't really have an answer. So let me try to find out more and I'll get back to you on that. I'll just write notes in there when I get the chance to. Okay, so for now, let's just assume that this reaction does proceed, even though it might not be a major product. You might have more of an E2 product, but in general, this product is also not impossible. Okay. Why does it not show an O minus in? Oh, it does actually. Thanks, Sydney. It's right here. Okay. Okay, so let's consider the malonic ester synthesis first under acidic conditions. When you have under acidic conditions, okay, just look out for H3O plus and heat. When you see that, know that first you are forming a carboxylic acid, and two, you're cleaving half of the ester. So half of, I'm just gonna say starting material, right, which is here, and you'll see what I mean in a bit, okay? This is a good way to check your work. So the first step in this reaction here, okay, you have a strong base, right? Notice that it's Naomi and her homies. So grab a proton. Okay, and then attack the benzobromide. So what you have here, well, this is one step already, so. Okay, once you have the benzobromide, now step 3, remember, first and foremost, you need to form a carboxylic acid. Second of all, you need to cleave half of this part here. So this part where I'm highlighting in red goes away. You don't want that part anymore. So what you have in your final answer would look like this. And don't worry, I'll talk about the mechanism in a bit. Okay. Likewise, for the second step, you have the first reaction being what? A Fischer esterification, right? Right, it's a Fischer esterification. Why do you think it's important that we do this step though? Why can't I just take my base and say, let me attack this proton here? Yeah, because don't forget, you have an acidic proton here, right? An acidic proton with a hydrogen and alcohol. Remember, that's why Grignard is so alcoholic, right? Because Grignards are all bases, and this proton next to the oxygen is going to be acidic. So bases are going to deprotonate the hydrogen instead, right? And you cannot do that. So you have to sort of protect it in the form of an ester. So I'm using isopropanol. And now there are no more acidic protons, but in the form of the alpha hydrogen. Then Naomi and her homies can attack it. So what you have is going to be this here, and then you have this. And of course, remember that the last trick I taught you was make it a carboxylic acid and then cleave off half of the chain, right? Let me see. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, so this is your answer. Let's see this. Yes, pH is a phenol. Okay, so now this is an acidic condition, right? Oops, sorry, this is not notes on Aldol condensation. This should be mechanism. Okay, so let's look at the mechanism. I'm gonna do the second one. And I'm gonna start from the malonic ester. Now, this reaction is also called a decarboxylation reaction. Why? Because we're eliminating CO2 gas. So this is what you need to form in your mechanisms. If you don't see a CO2 at some point, you are doing it wrong. Okay, so let's go ahead and do this first. Okay, what kind of conditions do we have? Very good. It's an acidic reaction. So what would happen first? Nucleophilic attack or protonation? Very good. Protonation first. Same rules apply for all the reviews, right? If you have a mechanism to do, always ask yourself what is the first thing you're going to do. Is it a nucleophilic attack or a protonation? So we have an acidic condition. So it's a protonation, right? Okay, so the carbonyl attacks. And is this going to be reversible? Good job. Yes, because it's acidic, it's reversible. Okay, so what I have now would be and the carbonyl is arbitrary, so it doesn't matter which one you want to protonate first. Okay. So now you have a nucleophilic a very nucleophilic atom there, right? So water is going to come in as a nucleophile. I meant to say electrophilic, not nucleophilic. So water is going to come in as a nucleophile and do a nucleophilic attack. Oops. Okay, now this is similar to the formation of acetals and ketones. Sorry, hydrolysis of acetals and ketones, right? Where we have to make the R group leave. So in this case, it's the ethoxy group. It needs to leave. And how is it going to leave? It's going to make itself a good leaving group first. So it will attack the proton. It's an intramolecular proton transfer. Okay, to form this here. Okay. And then, what do you think is going to happen? Well, remember, we need a carboxylic acid, right? So your molecule should start looking like a carboxylic acid as fast as it can. And what's going to happen is that either hydroxy groups, either one of them, is going to collapse down to form a double bond to kick off the ethanol. So what you have here is a liberation of the ethanol. Here, right? Okay, so now we need to, we already have our carboxylic acid. We need to kick off the entire leaving group, the other half of the chain. So how is this going to happen? Well, so this is what you need to start asking yourself. Okay, how can I get rid of this chunk here, right? So we want to make them into good leaving groups. And how are we going to make them into good leaving groups? Well, the first thing that's going to happen is that this carbonyl is going to grab that proton that's from the carboxylic acid. That's why it's reversible, right? Because a lot of exchanges are going on. A lot of things can happen. So we have this here. So now this is a happy carboxylic acid. And this now becomes a good electrophile. Now, based on your gut feeling, what do you think is going to happen next? It already happened just now. Exactly. Water is going to come back into attack. Very good. Okay, so that's your nucleophile adding to electrophile. Right, and again, the same process repeats itself, where ethanol is going to be protonated. So it's going to grab this proton here. And this will become a geminodiol. Okay. Then the process is going to repeat itself in doing what? Forming the carbonyl double bond right here. Either one, doesn't matter. Kicking off ethanol. So again, bye-bye ethanol. And we have this here. Okay, so now we have two carboxylic acids, sort of, because we got this here, this here. Okay, so we have this. All right, we need to get rid of the other proton. Hey, don't forget it from our charges, right? And this is what's going to happen. Remember, this is where the decarboxylation step begins. Ultimately, what we need to do is to get rid of CO2 gas, right? How can we do that here? So this is what's going to happen. First, I'm going to have my my oxygen going down into, hang on, did I forget something? OH. Yes, and yeah, this is no longer reversible, right? Because remember, it bubbles out of solution, so you cannot capture that back and put it into your molecule. So it's gone. Once gases are formed, it no longer becomes reversible. Let me see, did I miss a step? No, okay, so hang on. Let me just get rid of that proton first, and then you can see what happens, okay? So this part here is just water coming in to grab that proton out. So you get two clean carboxylic acids. That's what you want. Okay. So this is the decarboxylation process. And what's going to happen is your alcohol, right, is first going to collapse down into a double bond, right? So this here collapses down, right? And this is the carbon where it's going to form CO2. So in doing so, then CO2 is liberated. Then this is 1, this is 2. I form a nucleophile in the form of the oxygen, and then that becomes nucleophilic, right? So it's going to grab that extra hydrogen proton. That's step 4. Do you guys get that? So what I have at the end then would be this here. Okay, I'll show it again in 1 second. Okay, all right, let's repeat. I'm going to repeat again. So you have your carboxylic acid, right? We need to form what? CO2. So let me draw out the explicit carbon here so that you can see what I'm talking about. Right, so CO2 looks like this here, right? This is where the 2 oxygens are, so we need to get the chunk out. When we get the chunk out, we need to first collapse our double bond, sorry, our lone pair into a double bond, right? And then this would be able to be expelled, right? But do you see I'm starting to form an enol, or enolate rather? Then what happens is that I form a nucleophile, and then this becomes temporarily negatively charged. And then what happens is I grab this proton here. Okay, so yes, sorry, this should be OH. Right here, do you see that you have an enol? happens? What are enols good at doing? Tautomerizing, right? So we want to form the keto form, which is a lot more stable. And you can just show tautomerizing, that's fine. Okay, that's my product here. So in the exam, if you are given a mechanism, you will be given from, let me see. I've seen this in the exam mechanism before, so please take note. Yeah, if let's say you were given the same example that I did in the top, then you will be given step 3 to work with for your mechanism. Okay, that is what exam 3 is going to be about. What about the arrows, Jaden? Don't forget, tautomerization is a reversible process, although it very much favors the forward direction. Oh, well, if you really want to draw the arrows, then it's just the simple whoop, collapsing of a double bond. Then this becomes a nucleophile to grab that photon there. Because tautomerization by default in nature exists as a ketone and an enol form, right? So it happens like that here. It's not really resonance. It's more of a reversible thing. So yeah, by default, this just happens. That's just because how nature works. But in orgo, we care more about the keto form because the keto is a lot more stable. All right, so this is the step under acidic conditions, right? You can also have a malonate carboxylate acid under basic conditions. And what here would tell you that it's basic? Of course, you have to have a base, right? I don't know why they need to put that step in between when you can have just gotten away with just step 1 and 3, right? It doesn't make sense for me to add an extra step, but that's what people do apparently. So that's why we learn it. So just take note, the only thing that they might want to ask you is how does a base differ, right? So in this case, we're not going to do a nucleophilic attack. We're not going to do a pronation. Rather, we are going to do a nucleophilic attack. And the product that we get is going to be exactly the same as what we saw earlier on. Okay, so isopropyl. What we have here again, this should technically be the E2 product, but let's just go ahead and put that first. Then we'll figure it out later. Okay, and then KOH. What does KOH do? It's going to make it into a carboxylic acid, and then H3O plus is going to get rid of half of that chain, right? So same thing, your product is going to look like this. S is the same product at the bottom, right here. Okay, let's consider the mechanism. I'm going to do the mechanism for this one here, so just take note. Okay, so basic conditions, right? Nucleophilic attack happens first. Okay, so again, you will be given the starting material from step 2 already to work with, so don't have to worry about that. All right, who is our nucleophile in this case? Anyone wants to make a wild guess? Yes, it's going to be in the form of a hydroxy group hiding in sodium hydroxide, sorry, potassium hydroxide. right? So OH minus is going to be a nucleophile and it's going to attack the electrophile. Okay, but don't forget, small bases like that. Naomi is reversible, as is sodium and potassium hydroxide. So it's also going to be reversible here. Okay. So right now we have an alkoxide and we want to make it a carbonyl again. Who's going to leave here? Who's a good leaving? Yes, thank you. So a ethoxy group is a good leaving group. And what we have here is OH. Okay, but this time is a little bit different. It's no longer a proton transfer, right? It's more of a, again, we are going to get an attack of sorts. And whoever you kicked out is going to come back for revenge through this attack here to form my enolate again. So what we have would be this here. Okay, and don't forget your R group. So what do you think is going to happen here? Well, we need to make them equal, right? So another hydroxy group is going to repeat itself to the other side. And this is why it doesn't matter. Yes, basic conditions also use reversible arrows because potassium and sodium hydroxide are reversible bases as well. Okay, so what are we trying to do here in this step is to make the left look exactly like the right. Okay, so technically everything repeats itself where you have a collapsing of the lone pair to kick off the ethoxy group. Okay, and then you have the carboxylic acid. Sorry, I don't know why I keep drawing that. Right here. Okay, anyone remembers what happens next? The ethoxy group comes back for revenge to kick off right here. So we have now the left looking exactly like the right. Okay, and then we are going to start a decarboxylation process. We need to form CO2. So let's start preparing our molecule to form CO2 first. What we have would be H3O plus. Okay, and then we need to form a carboxylic acid, right? Sorry, a carbonyl. What am I talking? Carbon dioxide. So right here, well, what was the driving force? Formation of CO2. Where is it hiding? In here. It's going to collapse down, forming a carbonyl again, sorry, an enolate, going back up into an alkoxide. And then when it's temporary nucleophilic, it's going to grab that proton. Okay, and this step is no longer reversible. Remember, once your gas bubbles out of solution, there's no way to capture it back, right? So this is OH. Right here, you have my enol, and right here. Okay, and right here you have sort of an enol as well. So don't worry about it. Just go ahead and tautomerize into my final product. So we have 1, 2, 3, 4. I draw an extra carbon. Let me show all 4 arrows as one step. Yeah, I think you should be able to do that. Okay, so 1, 2, 3, 4, 1, 2. There we go. Okay. A funnel ring? David, where do you see a funnel ring here? Do you mean the previous one? Which one are you talking about? I did not get rid of a carbonate bonded to the phenyl ring. And okay, why do we need H3O plus, Laura? Because it's for the decarboxylation. So this is step 3 here. What I put here for step 3 is right here. This H3O plus right here. You need a proton source. Don't worry if you can't keep up with the notes, David. Well, this is going to be up on the Google Drive after lecture, right? So is everyone else here doing okay? I realize it's been almost an hour already. So there's no way I'm going to be able to get through all my notes today. I'm not going to kill you guys. All right, so let's move on to our next type of reaction. It's called alpha halogenation. And before I even fill in the blank, what kind of conditions? Oh, all right. Yes, Katie, go for it. Before forming CO2. Because don't forget you're dealing with a reversible base. And why is it before forming CO2 is irreversible? No, you caught me there. Good job. Okay, once you form CO2, it's no longer reversible. Then when you tautomerize it, it's going to become reversible again. Although it's a good habit to take note that this direction, the forward direction, is very much more favored than the backwards direction. All right, can we use hydroxide for the alpha halogenation? No, because this is governed under acidic conditions. Okay, so this is the standard form of reagents that you need to write. What's the first step? Anyone remembers? So honestly, you can get away with just putting H3O plus. You don't have to put KOH, but if you prefer basic condition, then you can do it that way. But honestly, it really does not matter. You can just put H3O plus. You just, by nature, make it acidic, and that's fine. Yeah, it's the Swern oxidation. Good. Okay, and then now that's where your alpha hydrogen's hiding here. Right? So it's an alpha halogenation, right? So either of these two here are alpha carbons. What does this mean? Your halogen better be in the alpha position. Okay, alpha. Same thing for the bottom one. Well, this here is already substituted, so you can't go there. So this leaves for only here, right, to be the alpha hydrogen or the alpha carbon. So what we have would be phenyl. And notice that whatever I have here, right, would be the corresponding acid. So be careful. Do not use Br3 and put Cl2. Don't do that. But the fact that you have a halide, right, tells you that you need to put a halogen in there. Okay, and then I can do a simple SN2 type reaction, right? Remember in Argo 1 we saw? Don't you miss these kind of reactions? I think Argo 1 should be doing this right now already, or maybe even past it. Okay, and then H3O plus. What does H3O plus do? Anyone remembers? This is from exam 3. Yeah, it's a hydrolysis of a nitrile. So what we get is a carboxylic acid. Right here, okay? Let's consider the mechanism, shall we? So I don't know if I'm able to go through Aldol condensation. Ideally, yes, I will be able to finish Aldol condensation today for sure. I might stop at the Claisen one, just because, yeah. Well, we'll see how it goes, okay? I have another hour to go, and I'm just gonna pull through until I get as far as I can. So what we have here is an acidic condition. So bells should be ringing in your head right now on what should be done first, right? H plus, grab that proton. Right, and then this is where you have the hydrogens here, your alpha hydrogens. Now remember, even though we don't show it there, but it's already implied, right? That if a halogen exists as a diatomic molecule, and what it can do is to break apart, right? It can dissociate under various solvents, right? If we put it in its corresponding acid solvent, then it would dissolve and it will just break apart. So that's why we can just show, for example, bromine coming in to grab that proton. And because this is an acidic condition, it will be reversible. Right? So we have the enol, and then the enol is going to come in to grab another molecule here. Oops. And of course, the last step is going to be irreversible because the other remaining molecule of bromine is going to come here to grab that proton to give me my product here. And that's the alpha halogenation process. Okay. Same thing happens if you have chlorine. It's just instead of bromine, you're dealing with chlorine. The mechanism the air pushing is exactly the same. So if I can't finish it, right, I will have to continue it next Sunday, and then I'll combine it with amines. But I think I should be able to get through a good chunk of it. I mean, I'm at slide 9 right now, technically halfway, so should be okay. If on the first question we put on the BR on the other side, would it be wrong? Oh, no, don't forget because they're equivalent, right? So it doesn't matter which side you choose from. As long as the molecule is symmetrical, you'll be fine. All right, now we're going to talk about the haloform reaction. Haloform reactions form carboxylic acids. Formation of carboxylic acids, which means that whatever R group you have here and here, you just have to replace it with an OH. Right, so same thing for this one here. Right there, okay? You're forming a carboxylic acid. Why? Because you have a strong base that's able to deprotonate, right? This is, instead of using Naomi, we're using a small base here, okay? So don't forget, potassium hydroxide is a reversible base. Okay, and why do we need halogens and water? Well, halogen is to make it acidic and good leaving group. And then the water is to protonate it, source of H+. Okay. It's always a terminal one. And I'll show you why later on. Okay. When we consider the mechanism. Okay, so oops, it's not. Okay, so CH2, H, right? So remember, it's a strong base in the form of a hydroxide that comes to grab this proton to form my weight. See, this is my weight flex. I know I'm doing it right. If you don't have any weight, then you will not, you're not on the right track, right? So first step, done. Second step, bring in your bromine. So that you form this here. Okay, now here's what you can do. This step is going to repeat itself 2 more times because we are replacing all these hydrogens here with the halogen. Whoops, not 3 times, this is 2 times what we have here. Then becomes CBr3. Now, in this case here, why we get a carboxylic acid is because CBr3 is a good leaving group, right? And it will only work for CBr3. If you have CRBr2, for example, if one of them is not, it's just a random R group, it will not work. You need to have 3 bromines, and this is the only spot that can give you 3 bromines. So typically, it's always going to be at the end. Okay, it will always be at the terminal methyl because you have 3 hydrogens, which you can substitute for 3 bromine atoms. Oh, okay. Thanks for letting me know. I just got it back in. So the 2 times part, technically yes, but you don't have to show it in there because it's just repeating itself twice, right? So everything that's happening in between it is also implied that it's reversible. Okay, so then my base is going to come back. So don't forget you have more bases than halogens, right? So another base is going to come back. To conduct an electrophilic attack. Sorry, nucleophilic attack. What am I doing? Okay, and what we have here would be this here. So O minus OH. Okay. So don't forget CBr3 is a good leaving group, right? Better than hydroxides at least. So what we have here. Now this part here becomes well, it technically becomes irreversible. But here's the thing. How acidic do you think this guy is? David says it's low in acidity. What about everyone else? What are your thoughts? Hydrochloric acid is acidic, right? I have no idea really what the pK is, but because I know it's 3 electronegative atoms, right? Can you imagine the carbon here? How much electrons are going to be pulled away from it? So of course it's going to be super acidic, right? Yeah, it's going to be very high in acidity, which means it makes it a strong acid, right? And what do acids do? They have the potential to grab a proton, right? So that's why we need to put in water because this is going to happen here. And this step is reversible. Right? Do you see we get a carboxylate? And this is why we need to put in the proton. We need to give it in the form of water or an acid. You might see H3O plus. That's also okay. Right, so we need to push it in acidic conditions to make my product here. Okay, and this is how I get my product. Make sense? Okay, so up to this point, we have covered the malonic ester. We've covered the alpha halogenation and the haloform reaction, right? So now we're going to talk about the Aldol condensation, which is a really big topic on its own. It's so big that they swap out NMR in exam 3 for a transition state of this question. Okay, and I'll try my best to teach, especially for those who are in Dr. Molina's class, because you have not seen this technically. So if I'm confusing you, please let me know. For those who are in Dr. Driver's class, he's already gone through this, so let this just serve as a refresher for you. Oh, thank you. Yes, so this should be very good. An acid chloride, because we go through this route here. exam 2. Thank you. Okay, so it's really crucial that you understand whatever is going through in here. If you don't, definitely stop me and I will try my best to explain it, okay? Now, honestly, I get nervous teaching new stuff to you guys just because that's your professor's job and not mine, but it is what it is, right? So, okay, what we have here is what kind of base? Can you see? Irreversible, and it's what? Kinetic, right? Okay, so we always need to have an irreversible and kinetic base, which is LDA, or you might see KHMDS. I don't know if Dr. Driver mentioned it, but Dr. Molina definitely did. You might see either or, but honestly, 99.5% of the time, LDA. Okay, so what would happen is that you need an irreversible kinetic base, and really importantly, you need an aldehyde. No aldehydes, no aldol condensation. That's the long story short, okay? And what we have here, I mean, I'm gonna talk about why we get this product, but what we have here, well, my base is gonna grab this proton to form my enol. And notice that my alkene is now anti with respect to oxygen, right? It's anti. And then when I bring in my aldehyde, it's just gonna do a simple nucleophilic attack. And then, of course, it will have an acidic workup. All right, if you do this on the exam, I think you're only gonna have the credit. The full credit comes in determining what the stereochemical outcome of these two substituents are. Okay, and this is what we're gonna consider. If we have a small group, usually alkyl groups, right? So C2, oh, sorry. If you see methyl, ethyl, isopropyl, methoxy, ethoxy, so on and so forth. These are considered small groups. Okay, and what do small groups give? They give us enolates here. As you can see, it's always with respect to the oxygen. So don't let that confuse you. It's anti, and what we have as a result is the anti-product. Okay, so our group, right, would have something here, and the alcohol will always be anti to it. Okay, this is something that we're going to consider through the two transition states, and vice versa for big groups, right? So if you have big groups such as phenyl, two R groups attached to a nitrogen. What else? You have, of course, phenyl derivatives. If you have, I think these are the only two they're going to encounter. Oh, terbutyl as well, right? They're going to give you Z enolates. So how it's going to look like is if you have a phenyl here, our group, as you can see, is going to be Z to it. So always remember, I'm going to write a note here. Alkenes are E or Z with respect to the alkoxide. So it's the O- atom. Okay, don't let it fool you in the exam. Driver had a pH as small group. Okay, that's pretty interesting because when I took it as a student, it was considered a big group. Let me confirm that, okay? Let me confirm that and I'll let you know. But as far as I am concerned and I know, it's considered a big group. You don't have to worry about the minor product. You have to care about the major one for sure. Okay, the major one's what's going to be in the answer. So this cyclopropane is considered pretty much a small group. So what do small groups give us? The anti-product, right? So, yep, through the E enolate, we get the anti-product. So what we have here would be isopropyl. And always remember, it's the R group that's to the left of the carbonyl, right? The one that does not really have an alpha proton sometimes. If it's a phenyl, then it's really easy to identify. But most of the time, don't forget, because it's a kinetic base, it's going to go to the least substituted site. So that's why it's always going to attack. It could be, I mean, technically, if you drew the enantiomer of it, it's fine. As long as you show an anti-relationship, you're okay. All right, so likewise, if we have a big group here, and we have that, okay, so we have to ask ourselves, do we have a irreversible kinetic base? Yes, okay, do we have an aldehyde? Yes, so we know we can proceed with an Aldol condensation. But because this time we have a large group, right? So what we're gonna have is the Z olefin, or the Z enolate. So, and butyl is gonna be here. Now remember, it's Z with respect to the oxygen. Okay, then I'm gonna take my aldehyde. To form alcohol. Right? So when I draw my answer, it's gonna be syn to each other, right? Because it's a large group. So we have OH right here and down, syn. So this is anti, and this is syn. Yes, the small group here was the cyclopropane. But I think in the next few examples, I gave you really explicit ones like methyl, right? And big groups like the vine red one. Okay. All right, so why do we get the syn and anti-product? Is because of two very big transition states. And this is what you're gonna see in the exam, okay? This transition state is called the Zimmerman-Traxler transition state, where we have the first one being this year and the second one being this year. As you can see, I've already given you the template. And this is what you're gonna see on the exam. But for quizzes, right, you might have to draw it on your own, as it was the case with the Kumada and Suzuki cross-coupling cycles, right? But if you don't know how to draw it, remember, ultimately, you guys are taking the quiz from home. You have something to refer to. Put the piece of paper over mine, trace it out, and you're good to go, right? But if you have this question on your exam, it will be given to you already. They are even kind enough in the exam to give you the boxes, which I did not draw it here. I'm gonna want you to draw it on your own. Okay, so let's consider the first transition state. We know that this here is a small or big group. Remember, it's always to the left of the carbonyl. So is that a small or a big? It's a small group, good. So what we have here would be an E alkene, right? Isopropyl. Okay, so what you need to do here is to find where this enolate is going to look like on the chair. Okay, so right here. So this is right here. Don't worry, you'll be given boxes in the exam, so you'll be able to identify them. Okay, so you have a box here, you have a box here, and you have a box here. Okay, so this is your structure. Now, what kind of alkene did we have again? We have an E alkene, right? So with an E alkene, do you see that it's right here in purple? So take your colored pencils, your crayons, your markers, and whatever. This is what I did for my exam, by the way. Okay, so take it down, and then you're gonna wanna trace it and follow the same configuration. So should I go to the right or to the left to get my E, enolate? You should go to the right, exactly, because this is where it takes me to the isopropyl here. So then this would have to be methyl, right? Okay, I'll use a darker marker for the next one. All right, so what do you think this last box is gonna be? Hydrogen, very good. Okay, let's say you got it wrong, right? Let's say you did this. So you put isopropyl here and you put hydrogen here. Remember, by default, does nature prefer the E or the Z alkene? Yeah, it prefers the E alkene, right? Remember, a trans configuration is always lesser in energy. So by default, it will be in the E olefin, right? So what we have here originally was this here, right? As you can see, because these two groups are small, methyl and isopropyl, they are not gonna compete with each other, right? The Gaussian interactions is not gonna be too harsh. So that is fine. It's gonna remain as it is. However, if you swap it, if you put isopropyl here, right? Yes, it seems better, but don't forget that isopropyl and oxygen, first and foremost, can interact here. Second of all, I'm not gonna get the E enolate. I'm not gonna get the E alkene. So as what Asim was saying just now, you would end up with the Z olefin, and that's wrong. So always check your work to make sure you're doing it correctly. If you are supposed to get an E olefin, make sure you get the E olefin on your transition state there. Okay, and this is why I always tell my students, always bring a marker or a colored pen so that you can explicitly trace it out on the chair and you will never go wrong this way. So you're looking at the first transition state to assign your configuration. Okay, the methyl in green, right here, it's right here, right? And then the isopropyl is going to be right there. Any questions on the first transition state? Oh, by the way, if Dr. Driver taught you guys the Ireland model, that's not going to be considered as part of the course. So you won't see the Ireland model. You're only going to do with the Zimmerman-Traxler. Everyone understand this? Can I move on to the next transition state? Okay, good. So we know that this is now going to be a good nucleophile in the form of an enolate rather, right, to attack my carbonyl here. And this is where it takes me to the second transition state on the chair. Okay, here's how you break it down. On the left of the chair is the enolate phase. And on the right of the chair, you're gonna have, let me use a more different color marker. The aldehyde phase. Okay. When you get your exam, first things first. So remember in exam 2, what I told you to do, go straight to the NMR and see if there's a Birch reduction. And if it's a Birch reduction, what would happen to the NMR? Would it be successful? Fail. No, right? So same thing for exam 3. When you get your exam, go straight to this page and put the hydrogen right here. This will always be the case because we have the aldehyde, right? Let me use a color marker for this, and I'm going to show you what I'm talking about. Okay, so the aldehyde is right here, right? It's just light. Oh, this is too light. Let me try this marker. Can you guys see this? Okay, this is where my aldehyde is. Right here, and right here. Which one is going to be better? A hydrogen in the axial position or cyclopentadiene on the axial position? It's of course the lighter molecule, right? Less sterics, exactly. So go ahead and always put the hydrogen there, and this will always be the case. Even with corona right now, yeah, it's still going to be hydrogen right there in the axial position. Okay, you could have COVID 2025, it will still be there. You could graduate and get a PhD from like 10 years from now, it will still be there. Okay, it will always be the case. Why am I stressing on this so much? Because in my exam, I did this. Well, I think it was my TA, Dr. Molina, that told me, all right, always remember H is axial. You know what I did? I wrote this down on the exam and I put hydrogen right here. So that's a big oof. Please don't do that. Don't make the same mistakes that I did. Always check your work and make sure it makes sense. Okay, this is axial. So this is the aldehyde phase. That is 2 points there already, right? Let's move on to the remaining boxes. Yes, so hydrogen is always axial. Always, always, always. Okay, you will be given these boxes here. Okay, so remember, follow your enolate phase, right? So I'm gonna have to use the same purple marker that I used just now. Let me see if I can find a darker shade. Okay, this should be a little bit better. Okay, so remember your enolate phase. What was the configuration that we saw in the first transition state? E, right? So start from here, go here, and should I be going up or down to get my E alkene? All agree that we have to go down? Which means that isopropyl is going to be right here. I said E for small, Z for big. Okay, so this is a small, so we get an E alkene. So this is where the isopropyl is. Can you guys see that? I am not moving on until everyone gets this, okay? It's pretty much worth an NMR question. I think it's like 10 points or 12, something like that. So these are easy 10 points, take it. Okay, now, same thing for the green methyl. Where would that methyl end up at? Follow what? Your enolate, right? Go down, and then I don't have to go the other way, so I'm gonna go left, which is down here. So methyl is gonna end up right here. So what do you think the last box has to be then? Exactly, hydrogen. Okay, so now I'm gonna use, it's gonna look really colorful. Oh, okay, thank you. Yeah, just let me know, and I'll just let her in. Okay, so let's check our work. Why do we get the anti-product? Remember, oh, by the way, there's a mistake here. This should be isopropyl, not methyl. Change that. Okay. Do you see that the methyl down here, sorry, the isopropyl here and the oxygen here, because this oxygen is going to be what forms the alcohol, right? Do you see that they're on one's up and one's down? And because of that, that shows us the anti-relationship in there. So when you write your answer, well, you might be given this in the exam where they give you the exact template and then you have to fill in the wedges or the dashes. Everyone got that? Because I'm just copying what I did from the first transition state over to the second transition state. Okay, so the first transition state, whatever was in purple, right here, it was an E alkene, right? Which means that on my left is going to be the enolate phase on the second transition state, and this will always be the case. The enolate's always on the left, the aldehyde's always on the right. What you want to show is the same stereochemistry, which is the Z alkene, because if you went up, you would end up with the the Z alkene, so that's wrong. Okay, don't forget hydrogens are implicit, so they will always be there. Technically, you should have, this is where your alkene is, right? Okay. And then remember, to the left of the starting material is where you determine your big or small group. And this will be to the left of the carbonyl, which is right here. So in this case here, H is, there will always be a hydrogen and there will always be an R group, right? You just have to figure out where the hydrogen and where the R group goes. But in our case, because we have seen that it's going to be an E alkene from here, right? We are going to translate it back in here. And that's why we know that the hydrogen is going to be axial and the isopropyl is equatorial. Make sense? Can I do the next example and I will show you clearly where I'm trying to get the thing, okay? Yeah, so if it's an E alkene, then you're gonna get an anti-configuration because look at where the yellow ones are. Isopropyl is at the bottom, the alcohol is at the top, right? They're on the different plane, they're on different faces. So that tells me it's anti. Okay, I'm gonna do the next example where I consider a big group, and then hopefully that will solidify the information a little bit. If not, then I will have office hours again this week, and I'm gonna do a lot more practice problems on this. So definitely sign up for those if you want. I will have the registration open after class. Okay, so what we have here, of course, is a big group, right? Let's ask ourselves what kind of enolate are we gonna form first? E, Z, Z, good. So we are gonna form a Z enolate, and what's our final product gonna look like? Syn or anti? Syn, good. Okay, so this is what we need to work towards here, right? This is the big picture. Let's go into the molecular level to find out what's going on. So LDA grabs this proton here to form my first intermediate. Okay, remember it's a Z alkene with respect to which atom? The Vinram amide or the oxygen? Good. Okay, so let me go ahead and do this here. Okay, this green one here tells me that it's a Z olefin or Z enolate, right? And what we have now is our aldehyde. So let me collapse the lone pair down to form the good, to make the alkene a good nucleophile. and form the reaction with the aldehyde, right? So what we have here would be, okay, so we know that it's a syn product, so isopropyl, and the alcohol is going to be here. Like that, right? That's my final ring. I'll clean it up later a little bit, but we know it's going to be the syn product. Okay, let's consider the first transition state. Remember, boxes will be given to you on the exam, but for now, I need you to be able to identify where these boxes are coming from. Okay, so it's going to be this carbon here. Oops, let me grab that marker again. Okay, now remember, the first thing you want to do is to find out where the Z enolate is, right? So take a marker, start from oxygen, let's trace it together. Going it here, going down here, and going back to the left or to the right to get my Z enolate. Yeah, exactly, we're going to the left, right? Okay, so you see this is where my Z enolate is. So what would be the R group I'm going to write there? Isopropyl, very good. Okay, which means that the one on the right has to be what? Very good. Don't forget implicit hydrogens here. Okay, and then what would be the box that I'm gonna fill right here in orange? The N group, exactly. The Weinreb amide, so right here. Do take note that there is a possibility in your quizzes and exams that they leave this box blank here. Okay, and that will always be LDA, always. But for the most part, they usually give it to you. That's why I put it in there. But if they don't, just take note that LDA will go into that first transition state. Okay, does everyone get the first transition state already? Now, ask yourself what would happen if you swapped out the R groups, right? So if hydrogen went here and isopropyl went here instead, right? Do you see that this big group here is in the way? I'm going to be a bit dramatic. And then what will you encounter here? See, strong Gaussian interactions, right? And that's bad. That's why nature has no choice but to conform it to the Z enolate. Very good, Kay. Can I go on to the next transition state? Okay. Now, for the next transition state, what is on the left of the chair? What phase is that? Thank you. You see? The enolate phase, and then on the right has to be the what? Aldehyde phase. Good. Okay, so remember, first things first, go down to this box here and put, thank you, which means that this box here has to be the R group, right? Can everyone see that, or do you need me to mark it out with the marker? Right, because it's right here. So this is right here. So technically, you're looking at the aldehyde from here, right? If you want to see it in 2D. Okay, now let's figure out the rest of the boxes here, here, and here. Okay, again, take your marker, if you have one, or pencil, whatever you're using. Okay, we want a Z enolate, right? So if I go down from here, if I always start from oxygen, go down from here, go back up here. Now, should I go up or down to get my Z enolate? I should go up. Okay, let's go up then. And what would be in here? Isopropyl, which means the bottom one has to be hydrogen. Good. And then what about this one here? Remember, you have one more line that's unshaded, so I'm going to put it in here, and that would be my primary, my end group, right? You guys see the pattern? It's always the same, no matter what we give you, right? You just have to identify the substituent if it's big or small, and everything else remains the same, right? Everything else will fall in place. Am I making sense so far? Because this is always the hardest part of like what people feel order to is, but honestly, it's really not so bad once you go slow, once you really approach it from a different point of view. Because professors like to use technical terms like diaxial interactions and whatnot. I understand that you guys are not really caring too much about that, right? So I will try my best to teach you this way, right? And of course, I use orgo concepts to help you check if your answer is right, like what I did just now. Remember the Gaussian interaction? That was not good, right? So always remember the aldehyde phase is where my OH is going to be. And you take another marker and ask yourself, okay, do you see that the isopropyl here and the oxygen here are on the same phase? This would be probably quiz 7 material, right? So because you're on the same phase, so therefore, what can you say about them? They're going to be syn, right? And this is why we have syn here. Versus the first one that we did, do you see that they were opposite sides of each other? They're anti to each other. So that's what happens as a result of a small group. But as a big group, you get the syn product. Questions? Oh, okay. Questions, comments, concerns? Okay, I'm glad that helped, Jacqueline. Okay, I really need everyone to understand this. This is a really important concept. I'm not leaving anyone behind for this. So if you guys are good, then I will move on. So that being said, please know how to draw these configurations by hand. If you don't know, I will put up a template on my website and you can download them. And if you ever need to use them for quizzes or what, you can just trace over it, okay? Does this sound good to you guys? Okay. All right, so, sorry, let's just let the plane pass. Give me 1 second. Okay, so you can also make an Aldol condensation with an irreversible base, such as Naomi here, right? But if you were to do that, you would have to have Naomi in my first step and Naomi in my last step. Okay, so this is technically also an Aldol condensation because we are forming an alcohol, right? So step 1, I will show you the reaction pathway. Step 1, what's tempo? What does tempo do? Yes, it oxidizes it. Okay, and then I'm gonna use Naomi and her homies. forget 2 hydrogens here, right? Okay, and don't worry about the stereochemical outcome for this because it's not LDA. So it does not go through the Zimmerman-Traxler. This only applies to LDA. Please take note, you cannot do Naomi and her homies or something in here. It won't work. Okay. And then what I'm going to do is to have an Aldol condensation here. So same process. Okay. Just draw it here. OH. Okay. What we have is this here. Okay, now here's the thing. When I introduce another equivalent of Naomi with heat, this is going to favor an E2 type of reaction to give me this product here. Okay, and how does this happen? Well, Naomi is a strong base, right? So bases deprotonate the alpha hydrogen. This is, so this is ethyl. This is the hydrogen here. Right? This is what we have from before. This is step 2 and 3. Right, so step 2, 3 comes down to here. Okay, so strong base takes away the proton right there. Why do the bonds in the ring not move, right? Namrata, if you, I mean, doesn't matter. This is just naphtha, so you don't have to draw 2 rings if you want. You can just draw 1 final ring and that's fine. Don't waste too much time on that. Okay, so as you can see, I did not draw stereochemistry here. And that is the reason why it does not happen is because we are using a different base, right? So in this case, ultimately what we are forming is an E2 product. It really doesn't matter what we draw. You don't have to care about this funky transition state. This is more error pushing based to get your final product. Okay, so strong base takes away the alpha hydrogen, forms my what? Enolate. And don't forget, Naomi, reversible. Terbutyl here, right? Okay, so what we have is a negative charge. Okay, so how do we get the E2 product is because the lone pair on the alkoxide is going to collapse down here, pushing this double bond here and causing alcohol to leave instead. Okay, so this is where we get the formation of the E2 product. Right here. Because you see this part here, resonance drove the double bond. Resonance drove the double bond to this carbon here. Let me draw it again, okay? Yeah, but don't forget that alcohols under basic conditions have a better tendency to leave. That's why you need heat, right, to push the arrow forward. It will not come back for revenge, no. Okay, so I'm going to draw it again. Alkoxide forms a double bond here. Then this alkene is going to go right here, kicking off OH. So what you have is kicking off the OH group here. Okay? And the last thing that can happen, well, I'm going to stop after this reaction here, just because I think you guys had too much for today. I'm not going to overkill it, and I will continue next Sunday. But for today, I will stop up after this cyclization process. So we'll finish Aldol condensations today. At the very least, for Dr. and Melina students, you will have also gone through the Aldol condensation and the transition state. So that will be fine. You will have the stuff ready to go for lecture on Tuesday. Okay. So what you want, okay. So whenever you have multiple alpha hydrogens, right? You have an alpha hydrogen here, and you have alpha prime here, right? What do you think, which do you think here is going to get deprotonated? Alpha or alpha prime? It's alpha prime, very good. Because, and this will always be the case, so you have to use your judgment in the exam and quizzes to figure out which one to use. Okay, because nature, not me, not your professor, but nature, wants to form the most number of member rings possible. Okay, and the only way that it can do that is if it deprotonates alpha prime. So when you do that, you would have this intermediate here. Ooh, do you see that enolate flex again? Oof, big guns. Okay. And what you have here would be this product. Right here. Okay, so remember, because I have more, why do I want to form more member rings is exactly what Jaden says, because you want it to be more stable, right? And if you imagine if you form cyclopropane, cyclobutane, right? All these are really strained molecules, so you don't want to form those. 5 member rings are a good way to start, 5, 6, 7, right? Nothing more, nothing less. Okay, let's look at the mechanism on how this forms. So I'm going to start with my starting material here. Okay, again, what am I using here? I'm using sodium methoxide, which is just another cousin of Naomi. So I'm going to form my enolate. Okay, and All right, and what we have here is our enolate. So I'm going to collapse my double bond back down. Sorry, my lone pair. And then the nucleophile is going to be the alkene that attacks the electrophile here. Okay, am I missing something? Yeah, thank you, Alexa. So from here, we have this here. Oops. Let me do it this way. Where did the arrow go? Okay, so let me number my carbons. 1, 2, 3, 4, 5, 6, right? So carbon 1 is where the alkoxide is. Carbon 6 is where I'm connected to this here, 2, 3, 4, 5, and 6. Okay. All right. From here, well, it needs to get a proton, right? And where is this proton coming from? Well, that's why we have ethanol in there to get it, to pronate it. Okay, now, are we done? No, right? Don't forget, this is a thermodynamic reversible base. So thermodynamic means that the methoxy group, or Naomi, sorry, in this case is methoxy, right? It's going to go back to grab this proton to form another enolate. Right? And with enolates, are alcohols good leaving group? No. So we need to push the reaction to completion using heat, right? So this step is where heat's required to push my alcohol out to get this product here. So I get my olefin here. Okay, and that's my final product. I drew it upside down, but let me just correct it. Okay. Any questions? I'm glad it's clicking for you guys. So do you guys see the pattern? So, okay, in terms of content, I think everything up to the Zimmerman-Traxler will be fair game. So I think if you sat through this review here, you should be good for the quiz. The last step with heat. Well, it's just a formation of the carbonate, right? Remember, always try to form the carbonate as best as you can. In doing so, this double bond here, this alkene is going to go down here, right? And then after that, carbon becomes tetrasubstituted, so it has to kick something off. And what does it kick off? Alcohols. Alcohols are bad leaving groups, right? So because you're bad leaving groups, you need to have a lot of heat to push it to completion. And that's why we get the product. Karen, which pattern are you talking about? The first step? Oh, yeah. So remember, if you have multiple alpha hydrogens, look for the alpha hydrogen that gives you the most number of member rings. If you have, let's say, a 4-member ring versus a 5-member ring, then the proton that gives you the 5-member ring will get deprotonated. Okay, all right, guys, so I'm gonna stop here today. And for office hours this week, I'm gonna go through examples from whatever I covered today. So if you wanna have a hands-on on how I'm gonna do stuff, definitely sign up for those. I will make that available like an hour from now. If you, yeah, okay, so how my office hours work, so it's already on the on my Google form. My hours are from Tuesday, Thursday at 6 to 8 p.m. online. Okay, and the link, I mean, you will still have to sign up, and I'll post the link as usual. So just think of it as a review, but it's not a review, it's just a time for you to ask me questions or time for me to do examples with you as we go along. Okay, quiz is on problem set 9. That problem set is also on my Google Forms. If you don't know any mechanisms, please look at the explanations that I have there. Okay, so because no one usually comes from my office hours, I don't have a cat for those, but I will cat reviews. Yes, please definitely email me. I'll be happy to have them, and I'll email and I'll reply you from there. You're welcome, guys. No, you need an alpha prime because, yeah, you never take away the aldehyde as far as you can. Good night, guys. Have a good night. Stay safe. Wash your hands. I'm going to go out for breakfast soon. Kind of weird being in a different time zone now. And yes, so give me a day to process a recording, and then once it's made available, shoot me an email and I'll reply you for there. Yeah, I'm back in Singapore now. Yep. It's 9:07 a.m. So nice. I mean, for those who are with me for the past week, you guys would know, I will always have my breakfast right after. Yes, I will be coming back to Chicago for sure. I'm only back home till there's virus things wear off. Okay, and even though I'm back in Singapore, it doesn't mean that I've stopped reviews. As you can see, you guys didn't even know I was back in Singapore, right? So as far as it's concerned, I didn't compromise on that. You guys can still have access to all the resources, the material. Now it should be here. It's my pleasure, Sydney. Okay, so this is page 9 and page 14.